So good morning to one and all, and welcome to VLSI class of unit number 4. So in the previous class, we discussed about some circuitry, that is the human body model and the machine model and the charge storage model. So, okay, these are the models to protect the IC circuits from the electrostatic discharge. So another, let us consider the protection network. So these are the electrostatic, to test in the previous class, we discussed about how to test the electrostatic discharge of the different models. Okay. Now in this circuit, we are going to consider a protection network. Okay. Protection network for those when the EEG network signals arrives, how to protect the our circuits. Okay. Let's consider the basically the protection circuit consists exists in the input output level with the pads. So they will be located. Basically it consists of diffuser resistor diode structures as shown in the figure. Okay, it consists. So here this is the diffuser circuit, resistor circuit. Okay, so here. Okay, so here the input resistance is from 1 to 3 kilo ohm. So, and this input voltage is in conjunction with the capacitance of capacitance in the diffusers and diodes and the gate structure in the input transistor that integrates and clamp the voltage level. We clamp the voltage level to certain safe level. Okay. So whatever the resistance we are using in this case, the resistance not only resistor. So we are going to use some capacitance that are exist in the diffusion and diodes and gate capacitance. Combinedly, this all combined with all these components clamp the input level to a shape level. Okay. So therefore, in that case, the RC time constants should be small, not to very small. Otherwise, what happens is the delay will be increased. So that will be very small. Okay, in this case. So depending upon, keep in mind, in this one we are going to design this protection network. Okay. Similarly, here the diode clamp signal level may be vary from 0.7 volts to VDD plus 0.7 volts. For example, this is circuit diagram of protection, simple circuit diagram of protection network. When the signal arrives here, and depending upon the voltage level of the signal at this point, so what happened? The negative voltage is entered. So when this transistor bit turns on, and the voltage is now equals to the cutting voltage of this transistor is 0.7 volts, and when the signal changing from 0 to signal changes, so what happens is the maximum voltage, the minimum voltage must be 0.7 volts when this diode turns on, and the maximum voltage is when this diode turns on. Okay, so therefore the maximum voltage in this case is equals to plus VDD plus cutting voltage of this transistor is 0.7. So that means the signal will be clamped to that level. When the signal low level will appear here, low level is appear at this point. Depending upon that, this diode will be turns on and these two diodes will be off condition. So therefore, we are getting the voltage is 0.7 volts. Okay, and when the voltage rises to some level, so what happens is when this diode will be turns on, this diode will be turns off, the output voltage suddenly shifted to the voltage VDD plus 0.7 of this transistor. So there is a signal will be clamps. Okay, the signal will be clamped to 0.7 to 0. That means the voltage at this point is greater than 0.7 volts, minus 0.7 volts, and less than VDD plus 0.7 volts. So like this, the signal will be clamps in this case. So similarly, another network we are going to, particularly here, have to consider to reduce the permanent damage to the diode structure, the current to the diode should be limited. Okay, so this limited value must be several tens of millivolts. Similarly, And in the previous case, we are going to use the resistor here. The resistors will be polysilicon series resistors we are using. So that can be in phase because of electrostatic electrostatic high electric field. Okay, that's why we are going to use the diffuse resistors. Okay, so that is the main thing. So another very important thing in this case, structure for improved version. Okay, the use of thick oxide NMOS transistors, which is shown in the below figure here. Okay, this is the another one is, and this circuit will be suitable for both human HBM and also MM. Okay, so this is holds good for both HBM, that is a human body model, and also the machine model. Okay, here we are using thick oxide transistors method. Okay, here we are having thick oxide NMOS transistors. By using the thick oxide NMOS transistor, we are going to use this production network. Okay, using the production network here. So that means we are going to use the extra transistor M1, M2, and M3 in this case. So here M1 is basically it is a thick oxide pulse through transistor, and M2 is a thin oxide NMOS transistor, and also M3 is also thin oxide NMOS transistors. And all these transistors will operate in the saturation region of the transistors. So here, the operating, all these will be operating in the saturation mode. Okay, all the transistors will be operating in the transistor mode. And whenever, for the positive transition, the threshold voltage of M1 and M2 should be vary from 20 volts to 30 volts. Okay, the threshold voltage of these transistors will be 20 volts to 30 volts. Okay, so that is about the production networks we are using in the circuit. Right. Next one, we have to concentrate now. Okay, now the input circuit will be here. Let us go for the next input circuit. So this is the simple circuit. The input transmission gate the inputs. This is the simple input circuit which consists of transmission gate with the activated enable signal. Okay, the circuit consists of transmission gate with the enabled transmission gate. Okay, we enable this is the transmission gate, and this is the production network. This is the pad. Okay, input pad. So the signal is entered into the pad and passes through the production network. Okay, so this is the functionality, what type of production network we are going to use. I've seen the previous topic. Okay, that is that type of production network, and this is the simple one, or maybe diffuse resistor, diffuse diode model, or maybe thick oxide use of thick oxide transistors, NMOS transistors. Okay, so now this is the signal to be entered into the pad. It passes through the production network. And when the output of the production network is given to the input cycle, and there is no electrostatic discharges in the cycle that can be signal be transmitted. Otherwise, the production network will stop the cycle before entering the cycle into the cycle. Okay, so therefore the production network is recorded here, and the signal is sufficient at this point. So that will be transferred to the transmitted gate. So depending upon the condition of enable signal, okay, the total block diagram is given here. Okay, the total block diagram input circuit is given. It consists, this is the input pad, and this is the transmission gate sector which enables. This is the enable signal, and this is the output of the transmission gate. So structure will be like this. Okay, the structure is given here. Okay, transmission gate structure will be like this here. With two NMOS transistor connected in parallel, one, and the inputs will be given here in this case. So here, just observe here, this is the low level enabled circuit. Whenever we can apply a low level here, the circuit will be enabled. Okay, so now just observe here, when the low level is applied, so this transistor will be triggers. Okay, So it's on condition, a signal will be transferred to the X. Okay, whatever the signal is there, it will be transferred to the X. When the high voltage is applied, so the transmission gate will be stopped working. Okay, no signal will be transferred from this point to X, input pad to the circuit. So therefore, now just observe here, this is the transmission circuit gate structure, and here we are going to apply this. We have to consider A, and here is A bar. Basically, we can consider here. Okay, maybe. So instead of getting A, no, not A here, it is enabled. Okay, so this is E. We are going to give E here and E bar. When E 0, so what happened? That means E is 0. So what happened now here? When E is 0, so here we are. This is the CMOS inverter circuit, and this is another CMOS inverter. We have two CMOS circuits connected in parallel. Okay, the output of this inverter circuit drives the input of another CMOS inverter, and the output of this inverter is given to the this point, enable points, and the output of first inverter will be given to the input of the gate, this N channel gate. This is the N channel gate, and this point will be given to the P channel gate of the transmission gate. So when the input is low level, when the input is low state, so what happens? You are getting the output is high here. This high voltage is given to the transmission gate. So you are the transmission gate. So this transmission gate will be, this transistor will be on. Okay. Similarly, because the high voltage appear here, so this is given to the transistor here, this transistor, and this transistor will be turns on. Okay, this transistor will be turns off, and this will be turns on. So the output goes to 0 level. So therefore, the output at this point will be 0 here. So this 0 enables this pre-channel transistor in the transmission gate. So this is also in on condition. Because both the transistors will be on condition. So what happens? There is a low resistance path is exists between these 2 points here. Okay, so therefore, this A signal is transmitted to the X value. Okay, so A signal will be transmitted to the X value when the enable is 0. Remember that point. So signal will be transmitted. Similarly, when the high signal is appear, so what happens? This point becomes low, and this point becomes high. So this low signal for the gate of the N-channel MOSFET, this transistor turns off, and for high signal, this transistor also turns off. So there is a high impedance state will exist. So no signal will be transferred from GA to X. Okay, that X will be entered into a high impedance state. So this is the simple operation of the input circuit. Okay, so it is given when X is equal to A. Okay, when X is equal to A, when E is equal to 0. Otherwise, E is equal to 1, for example, the X value, output value is equal to high impedance state. Okay, so that is the main important thing in this case. And similarly, if any unused input terminals is there in the circuit, it must be tried. It should be tied to VDD or VSS. Okay, if any chip input, unused chip inputs are present in the circuit, so that unused input terminals should be tied to VDD and VSS. Okay, using pull-up or pull-down transistors. Okay, using pull-up and pull-down transistors externally. So some input pad modules have, basically what happens is, some input pad modules, they have built-in internal pull-up and pull-down transistors as a active load, pull-down transistor as a resistor. Okay, because the transistors will be on current, which is having the resistance is approximately 2000 kilo ohm. Okay, there is the pull-down and pull-down. That means this is a particular case. So whenever we are not having any, whenever we are not going to use some input terminals, so that is called, we call it the unused chip input terminals, and these are connected to the VDD and VSS using pull-down and pull-up and pull-down resistors. Okay, pull-up and pull-down resistors formed by using a transistors. So some input pad modules have basically they are having built-in internal pull-up and pull-down resistor is having the resistance will be 200 kilo ohm to 1 mega ohm. Okay. Similarly, we have another inverting network. So we are considering this case. This is also we consider instead of using transmission gate, we are going to use this type of circuit also. Okay. So now here we are having the production network. That means the output, the input pad is connected to the CMOS inverter circuit through a production network. Okay, here the typical value of the input low is 0.3 volts times the value of VDD, and maximum value is 0.7 volts the value of VDD. Okay, that is a low state will be VIL, that is VIL, we are going to represent VIL, V suffix IL is 0.3 times the value of VDD, and VHL is VIH is approximately 0.7 times the value of VDD. Okay, for example, if we consider VDD is equal to 5 volts, okay, if we consider 5 volts, so 1.5 volts is input, 3.5 volts is the output, high state, respectively. So with the high 30% of noise margin. Okay. So the and then sometimes whenever we are using the circuit, the TTL signals received at the input, the TTL signals having the different logic levels compared to the CMOS logic levels. So in that condition, we required to change the signal from one TTL level to CMOS level. That is, level shifting is required. Okay, so that level shifting will be to have to consider in this case also. Okay, so in that case, so we required, basically we require the TTL signals which will drive the CMOS logic. That means here we require the adjusting the ratio channel bit of the PMOS and MOS transistors, so that we can get level shifting from TTL circuit to CMOS logic. So in this case, the output signal levels will be 0.8 volts low level and 2 volts for the high level. Okay, and the input voltage are less than are equal to less than or equals to 0.8 volts. So can be considered as the low level, and input voltage which is having greater than or equals to 2 volts, we can consider as the high level. Okay. So and after when the signal, the incoming signal is passes through. So after the input production circuit, the signal will be level shifted to a desirable level, and then it will be given to the input circuit. So that is the main important thing how to do. So basically, we are using the TTL drivers, level shifting between the TTL drivers and CMOS gate circuit can be achieved properly by designing the ratios between the PMOS and the NMOS transistors. Okay, this means the level shifting will be properly you can get by using proper design of PMOS and NMOS transistors at the receiving side of the CMOS inverter gate. So that is the case. You have to remember. Okay, so from this we can go directly to the next one. Next, another method we are going to use non-inverting type of level shifting circuits. Okay, so in this circuit, the level shifting is accomplished in the first stage, and then it is followed to the second level. Okay, so now just observe this is another level shifting circuit we are going to use in this case. Okay, so that means the signal is passes after the production network is transferred to this transmission this level shifting network for the TTL. We are assuming the TTL network in this case. So the TTL level will be shifted to this part here. So this is the symbolic networks of this TTL level shifting network. Okay, but depending upon the input level, the output will be shifted. Okay, so there is this type of circuit we are going to use in the input circuit, and similarly we are going to use this is called the non-inverting stage. Okay, this is non-inverting level shifting circuit. Similarly, we are having inverting another type of network we are going to use. There is inverting type. So in the inverting type, we are going to use the Schmidt trigger structure. So this is the form of Schmidt trigger structure, which uses 70 ohm pull down resistors at this point. Okay, so that is we are going to use now here. That is This circuit uses split trigger circuit and uses the pull down resistor. So here it provides the negative going logic threshold voltage of 4, negative going logic threshold voltage of 1 volt, and positive going logic level of approximately 4 volts when we are using the 5 volt supply. Okay, by using this production network, that is the level shifting circuits we are going to use there. This is the input pad with the symmetric gas circuit. Okay, we are going to represent this input pad to be like this. Okay, this is the symbol of the input pad. We are using the resistance circuit in this case, right? So that is about the input circuit. Next, we can go for the output circuits and also L noise. That is we are going to consider di by dt noise in the next class. Okay. Okay, nice one.